So, good evening, everyone. I'm Rahul. So today here we'll be discussing about today it's an online tutorial of the NPTEL course, physical and the just one second. Let me turn on my pen. Okay, yeah. So today we'll be discussing about the some extra tutorial problems based on the NPTEL course, physical and electrochemical characterizations in chemical engineering. This is a course offered by Professor Tamal Banerjee from IIT Guwahati. So yeah, so here we basically this is a course that deals with all sorts of physical and chemical characterization techniques that are generally being used in chemical engineering techniques, chemical engineering scientists, just not only chemical engineering people, but nowadays, these techniques are widely used from the scientists from the background of physics, chemistry, biotechnology, biology, or so. So these are very fundamental techniques, and in this particular lecture series, like there were 3 lectures this week, and here Professor Tamal was discussing about the NMR spectroscopy. So NMR spectroscopy is one of the very well established techniques that has its use in a very wide range of applications, and that has been used by all sorts of science, different kinds of scientists like with background from physics, chemistry, as I said, biotechnology, etc. So without further ado, let's start the class. So myself, I'm Rahul R. I'm a Prime Minister Research Fellow from the Department of Physics, IIT Kharagpur. So I'll be taking this online tutorial class, and for the past 2 weeks have been organizing these classes, and I was discussing few lectures. So these lectures will be available for you, your reference in future also. So kindly go through this question so that you get a better idea on the questions that will be asked for your quizzes or assignments or during your exams. So and now let us start our class. So here we basically proceed our class. Like I'll give you a question, then I'll give you a few minutes to think about the answers so that you can get a feel about the question itself, and then I will discuss the answer with you. So instead of just providing you questions and answer, I'll be like it will be kind of a discussion section where I'll initially read the question for you, then I'll give you a few seconds for you to think about the answer, then I will explain the answer to you after that. Okay, now let's start our question. So the first question is a very fundamental and basic question, and the question is, what does NMR stands for? So whole of this week is based on NMR. So we want need to know what NMR actually stands. What is this expansion of NMR? So I'll give you a few seconds for you to think, and then I will give you the answer. So I hope you were able to figure out the answer. This is a very easy question. So the answer is nuclear magnetic resonance. So it is a it is basically a nuclear magnetic resonance. So NMR stands for N and M for magnetic and R for resonance. So the answer is uh, nuclear magnetic. Just a second. Yeah. Okay. Nuclear magnetic resonance. Actually, this is a kind of spectroscopic technique. Spectroscopic technique in which you actually deal with some kind of spectrum, analyze some kind of spectrum it can be of any kind of spectrum. For example, in UV visible, you'll be analyzing UV visible, you'll be analyzing some UV visible spectrum. And if you're using IR spectroscopy, you will be dealing with some kind of IR spectrum. Similarly, NMR is also a spectroscopic technique, and it is basically nuclear magnetic resonance spectroscopy technique. Okay, so I hope you understood what this NMR stands for. Now let us go to the next question. Okay, the question is, which of the following is a basic principle of NMR spectroscopy? Alignment of electric dipoles to the external electric field, alignment of external electric dipoles to the external magnetic field, alignment of nuclear spins to the external magnetic field, alignment of nuclear spin to the external electric field. I can read you the question once again. Which of the following is a basic principle of NMR spectroscopy? First option, alignment of electric dipoles to the external electric field. You should specify external electric field. Alignment of electric dipoles to the external magnetic field. Alignment of nuclear spin to the external magnetic field, or alignment of nuclear spin to the external electric field. So which one is the basic principle of NMR spectroscopy? I can give you a few seconds for you to think about the answer. Then I'll discuss the answer. So I think you guys got enough time to think about the answer. So now let me discuss the answer with you. So the answer is the alignment of nuclear spin to the external magnetic field. So what happened is that every particle, subatomic particle, have some kind of spin, which is intrinsic property spin associated with it. So, and initially these spins will be randomly oriented. So, but when we apply an external magnetic field, these randomly oriented spin, maybe these are very randomly oriented spin, for instance, and these randomly oriented spins will when okay, just 1 second. This randomly oriented. So what I'm saying is this is a randomly oriented spin. This randomly oriented spin in presence of some external magnetic field. See, let me call it as P. It will either align along with this magnetic field, or it can either align against this magnetic field. So this alignment can result in some kind of energy change, and this energy change can be further analyzed to get a proper NMR spectrum. So in NMR spectroscopy, we actually, as I told you, like spin is associated with all the subatomic particles, but in NMR spectroscopy, we actually focus on the spin associated with the place. So As we apply some external magnetic field, we study how the nuclear spin get aligned along with B or against B, so that can cause some energy change, and that analyzing that we can get an idea about the NMR spectroscopy. So once again, the basic principle of NMR spectroscopy is the alignment of nuclear spin to the external magnetic field. This has to be stressed, it is external magnetic field. Okay, I think we are ready to go for the next question. And the next question is, spin is an inherent property of electron, proton, neutron, or all of the above. Okay, I can read you the question once again. Spin is an inherent property. Inherent property is a property that is inbuilt to something. Okay, it is like kind of inbuilt, that is already there to that thing. So um so spin is an inherent property of dash. Which of them has a spin as an inherent property? So the options are: first one electron, the second one is proton, then it's neutron, and another option is all of the above. So I can give you a few seconds for you guys to think about the answer. Then I'll discuss the answer with you. Okay, I think you guys got enough time to think about the answer. Now, let me discuss the answer with you. The answer is all of the above. So, as I told you in the previous question, spin is an inherent spin is an inherent property of all the subatomic particles. So this concludes that spin is an inherent property of electron, it is an inherent property of proton, it's an inherent property of neutron. So yeah, so this like charge, so we have another inherent property of car, which is called the charge. Just like charge, spin is also a very inherent property that is inbuilt to every subatomic particles. And yeah, so the answer to the question is option D, all of the above. Answer to the question is all of the above. All proton, neutrons, and electron have their own corresponding spin. Okay, now let us go to the next question. Calculate the spin number, calculate the number of spin state for oxygen atom with corresponding atomic number and mass number if the nuclear spin quantum number is corresponding to it is 5 by 2. So this is a numerical question, and I think you may need a bit more time to solve this one. So I will read the question once again. Calculate the spin state for oxygen 8 Sunday if the nuclear spin quantum number of corresponding to it is 5 by 12. So you have already given spin quantum number I is given as 5 by 2. With this information, you need to calculate number of spin states. Okay. Yeah. So I can give you a few seconds for you guys to think about the answer. Then after a few seconds, I will explain how to solve this kind of a question. So once again, in this question, it is given that I is 5 by 2. So this is an input given to you. And with this information, you need to calculate number of spin states. Okay. Okay, I think you guys were able to think about the answer. So let me discuss the answer. Which is the question was basically uh, you need to calculate the number of spin state for this particular atom if its corresponding nuclear spin number is pi by 2. So to proceed with this answer, you need to know the formula, and the formula to calculate number of spin states is that is equal to 2I plus 1. So this is the formula you need to use for this kind of a problem. And here, given that I is equal to 5 by 2, which implies number of spin states is equal to 2 into 5 by 2 plus 1. Cancelling 2 and 2, you get 5 plus 1 is equal to 6. Therefore, the number of spin states for this particular molecule O78 is 6. So this is a very easy answer or simple answer. And now you have to know is this particular formula, which is nothing but this one. I'm sorry, which is nothing but this one, which is number of spin state is equal to 2I plus 1. So suppose in a question it is given that the corresponding spin quantum number I is said to be 7 by 2. Then we can calculate the corresponding number of spin state has number of spin state is equal to 2I plus 1, that is nothing but 2 into 7 by 2 plus 1, that is nothing but 8. So this is a very simple formula, but this will actually give you a very good information about like how many spin state are possible for a particular atom. Okay, now let us go further move to the next question, which is so answer as I said is answer to this question is nothing but 6, which we have considered here. So let us go to the next question. The next question is the absorption energy in NMR depends upon dash and dash. So basically, the absorption energy of an NMR spectroscopy, NMR spectroscopy depends on mainly on two things. What are they? What are these two parameters, or what are these two things in which the NMR the absorption energy in NMR spectroscopy depends upon? So I can give you a few seconds for you to think about the answer. Then we will discuss the answer with you. Okay, now I think you guys got enough time to think about the answer. So the answer to this question is applied magnetic field and the nuclei nature. So the as I told you, in NMR spectroscopy, the absorption energy, absorption energy in nuclear magnetic resonance spectroscopy depends of majorly of two factors. One about the applied, applied magnetic field, which means like which includes the direction of magnetic field, or maybe the strength, or maybe I can call it as magnitude of the magnetic field, etc. And the other parameter which it depends is the nuclei nature, which means like what is the nuclear I value that we have already discussed in the last thing. So what is this nuclear, like what are the possible number of spin states possible, what are the possible transitions, etc. The absorption energy NMR spectroscopy depends on various nuclear parameters and nuclear natures. Also depends on the external applied magnetic field. So basically, the answer to this question is the absorption energy NMR depends on the applied magnetic field and the nature of the nuclei. Okay, now let's go to the next question. So there's actually a spelling mistake over here. So it's actually 4. For hydrogen nuclei, the energy gap in terms of electromagnetic radiation falls in which region? So for hydrogen nuclei, we have called hydrogen. Okay, so in NMR we basically deals with hydrogen and carbon. So yeah, so for hydrogen nuclei, the energy gap in terms of electromagnetic radiation falls in what region of the electromagnetic spectrum? Is it ultraviolet? Is it visible? Is it infrared? Or is it radio frequency region? Which is basically the RF region. So which of the following parts of an electromagnetic spectrum actually represents the energy gap for an hydrogen nuclei? So I can give you a few seconds for you to think about the answer, then I will discuss the answer with you. Okay, so I think you guys got enough time to discuss about the answer. So yeah, I'll read the question once again. For hydrogen nuclei, the energy gap is in terms of the electromagnetic radiation falls in what region? Is it ultraviolet, visible, infrared, or radio frequency region? Answer to this question is the radio frequency region. So this is a very low energy comparing to UV or visible or IR. Comparing to this, RF is a very low energy region of the electromagnetic spectrum. So this is because the transitions happening between the nuclear states that releases the energy while this NMR process is a very low, and that very low energy, which we can call at some delta E, which is can be related to some electromagnetic wave as h nu, where E nu stands for the frequency of light, and h is the Planck's constant. So this energy, which actually come out in form of an electromagnetic spectrum, falls in the region of RF. So the answer to this question is RF region, which is the radio frequency region. So I think you guys were able to answer this question. Now let me go to the next question. So yeah, answer to this question is radio frequency region, which is generally 60 megahertz. So I forgot to tell you this. The answer to this is basically 60 megahertz. So the radio frequency 60 megahertz. Okay. Now let me go to the next question, which is define Lamar frequency. So here already you guys can get an idea about what does this mean is. So yeah, I can give you a few seconds for you guys to actually think about the answer. So we need to know what does this Lamar frequency is. You need to get a definition for this. So I can give you a few seconds for you guys to think about the answer. Then I will discuss the answer with you. Okay, so I think you guys got enough time to think about the answer. So the answer to this question is the rate. Gamma frequency is nothing but the rate of precision of the magnetic moment of a nucleus around the external magnetic field. So suppose you have a nucleus, just like what it is shown in this figure. So we have this nucleus. So yeah, so this is a nucleus. This nucleus is having some kind of inherent magnetic dipole moment, which is given as this. Now, when this is exposed to some external magnetic field, which is shown in the dotted line as this. Okay, so due to this, this magnetic moment will actually revolve around this at a particular frequency. So this will revolve at a, you could say, let me call it omega. With omega frequency, this will actually rotate. So this rotation frequency, well, so this kind of a rotation is called precision. So you guys might have know about the top. So when we so the children used to play with this top. So so in the top will also actually put forward this kind. So when a top is spinning in the ground, it will also provide a motion which is similar to this, which is also known as the position. So this top will actually rotate with respect to some perpendicular axis, which is this, with the ground, and it will be in a it will move in this kind of a motion instead of rotating just like this. So it will actually precise over an axis. So this kind of precision. So when it comes to nucleus, you have the magnetic moment that actually precise around the external magnetic field, and this is external magnetic field. This is magnetic moment mu. So this is called the Lama frequency. Lama frequency is a very important parameter when we are talking about Lama spectroscopy. So I hope you guys were able to answer. So the answer to the question is Lama frequency is the rate of precession of magnetic moment of the nucleus around the external magnetic field. I hope you guys were able to answer this question. Now let me move to the next question, which is what are the main advantages of NMR? Yeah, we are dealing with NMR, so we need to know what are the major advantages that one get when using an NMR technique for their respective research. Yeah, so I can give you a few seconds for you guys to think, refresh what Tamal sir actually taught in the class. So just think about for a few seconds, and I can explain you the answer. Okay, I think you guys were able to get enough time to think about the answer. Now let me discuss the answer with you. The main advantage of NMR as nuclear. The first one is a nuclear partition function on application of magnetic field. The structure information about the molecules, the electronegativity, hybridization, and bond orders are taken care. Now, in case of proton NMR, the peaks obtained at different chemical shift owing to different chemical environment, and it is easier for identification. NMR is a quick process like pulse. There are two kinds of NMR basically. So the pulse-based NMR can be done within order of second. The quantification of mixtures and likely binding states through 2D NMR. So major advantages like you can get the structural information, we can get the information about the electronegativity, hybridization, bond orders, etc. And we can, with the help of this chemical shift, which we'll discuss in a very next questions, with the help of this chemical shift, we can get information about different chemical environment. And unlike many other techniques, NMR is a very fast technique, especially the pulse-based NMR, which actually happens in the order of few seconds. And also, we can get an idea, quantized idea about the different mixtures that is actually present in your sample, and we can also get an idea about the bindings sites available in the sample. This is basically done through 2D NMR, which also we'll discuss in the upcoming slides. Now we can go to the next question. The next question is, what are the main disadvantages of NMR? So earlier we discussed about the advantages of NMR. Now let us discuss about the major disadvantage of NMR. So I can give you a few seconds for you guys to think about the answer, and I'll discuss the answer with you. So, got you guys got enough time to discuss to think about the answer. So the question was, what are the major disadvantages of NMR? The answer to this question is the major disadvantages are mainly the dependent of magnetic field intensity to drive most of the peaks. So we need to have an idea about the magnetic field intensity to get idea of most of the peak. It is not suitable for ppm level detection, unlike HPLC or UV spectroscopy. So yeah, this is also very one of the major demerits, and depending on the specific nuclei or nuclei cover. So it depends on what kind of nuclei you are dealing with, whether it is surrounded by different number of electrons or like many other factor also depends when you are actually doing an NMR spectroscopy. And the signal to noise ratio is also very high, so you need to have effective sensors or detectors to get a good result from the NMR. So actually, the signal to noise ratio is comparatively high, and that for the relaxation of nuclei also plays an important role in NMR. So that is also act as a disadvantage for the NMR. So these are the basic disadvantages for an NMR spectroscopy. Now, the next question is nucleus of an atom with low electron density experience dash magnetic field. Okay, so this question is about how an nucleus experience the magnetic field applied to it because of the presence of electrons surrounding it. So suppose you're having a nucleus and this nucleus is surrounded by say n number of electrons, and how this number of electrons would actually affect the experience of this nucleus of this external magnetic field, say B. This is the question. So I can give you a few seconds to think about the answer. So what, like, how will this electron, will this, suppose we are having a very low dense electrons, low density of electron, how does this increase? Will the, will this, will this makes this interaction or maybe this experience of this nucleus about this magnetic field much more strongly, or yeah, no, much in a weaker manner. So think about the answer. I can give you a few seconds, then I will explain you the answer. So yeah, I think you guys got enough time to think about the answer. So the question was nucleus of an atom with low electron density experience dash magnetic field. The answer to this is a stronger magnetic field. So this is because there is something called shielding effect. Shielding effect that actually shields the nucleus from the external magnetic field so that the nucleus can experience only weaker or a stronger weaker electric field when the density of the nucleus is very high. Suppose we are having a nucleus and the number of electrons surrounding it is very high. So this revolving electrons would generate a current which would generate a magnetic field which would then cancel out this external magnetic field, and the resultant magnetic field that this nucleus would experience will be comparatively lower with respect to what the original external magnetic field was. So the answer to this question is the nucleus of an atom with low electron density will actually experience a stronger magnetic field when compared to the magnetic field experienced by the nucleus of an atom when there is a higher electron density. Okay. I think you guys were able to answer this question. Now let me go to the next question, which is in NMR spectroscopy, the dash is a resonant frequency of atomic nucleus relative to the standard in a magnetic field. The question is in NMR spectroscopy, the dash is the resonant frequency of an atomic nucleus relative to a standard in a magnetic field. I hope you guys actually understood what the question is. I'll read your question once again. In NMR spectroscopy, the dash is the resonant frequency of an atomic nucleus relative to a standard magnetic field. So this is some kind of parameter that you may measure while doing NMR spectroscopy, and that is actually the resonant frequency related to some standard magnetic field. Okay, I'll give you a few seconds for you guys to think about the answer. Then I'll explain the answer to you. I got you guys got enough time to discuss the answer. So the answer to this question is the chemical shift. So chemical shift is a parameter which is basically measured in NMR spectroscopy. So this so calculation of the chemical shift is one of the shift is mainly done during an NMR spectroscopy to get the idea about the different parameters. So the answer to this question is chemical shift. Going to the next question. The standard reference substance, it's actually substance. The standard reference substance that is used universally is dash. Or this is actually for NMR. So in NMR spectroscopy, what is the standard substance that is used as a reference point? So you measure this chemical shift. So actually here you mention about the chemical shift. We measure the chemical shift with respect to some standard material. What is that standard material? So I can give you a few seconds to think about the answer, then I will discuss the answer with you. Okay, I think you guys were able to get enough time to think about the answer. The answer to this question is tetramethyl saline, which is also called TMS. Just a second. The answer to this question is tetramethyl saline, which is represented as SiCH3 4 times. This thing is also called as TMS. So in NMR, we measure the chemical shift with respect to that of TMS. So if you have a scale and this side represent the TMS, we see how the shift happens. If the shift is somewhere here, we see this much of difference, delta difference with that of the TMS. So TMS is a standard reference point that is being used in NMR. The next question, now let's go to the next question. The next question is, for a particular proton, the shift from TMS is dependent on the intensity of dash applied dash field. So how does the shift from TMS depends on, not how, to what? What does the shift from TMS depends upon? So this is the question. So if something, some intensity, maybe it can be magnetic, electric, electromagnetic, or none of the above. Some of its intensity, one of the following examples, intensity, if it is varied, then that will result in some variation to the shift that actually happens for a particular proton. So what is that particular field? Is it a magnetic field? Is it an electric field? Is it an electromagnetic field? Or is it none of the above? So I can give you a few seconds to think about the answer, then I will discuss the answer with you. Okay, now I can explain you the answer. For the particular proton, the shift from TMS depends on the intensity of applied dash field. Is it applied magnetic field? Is it applied electric field? It is applied electromagnetic field, or is it none of the above? The answer to this question is applied magnetic field. So yeah, so this depends on the intent shift, depends on the, just a second, just a second. Yeah, the shift depends on the intensity of the applied magnetic field. So this is the answer. Now let us go to the next question. The dash indicates the degree by which proton resonance is moved away from the TMS. So yeah, in this question we need to know what actually indicates the degree at which a proton resonance is moved away from that of its reference point. TMS as a reference point. So how much? So dash indicates the degree by which a proton resonance is moved away from that of the TMS. So what is that particular thing? So I can give you a few seconds to think about the answer, and I will discuss the answer with you. Okay, I think you guys got enough time to think about the answer. The answer to this question is nothing but chemical shift. This we have already discussed. The answer is chemical shift. Now let us go to the next question, which is a chemical shift is expressed in dash of spectrometer's fundamental operating frequency. So what is that particular unit? Is it parts per billion? Is it parts per million? Is it parts per trillion? Or none of the above? Which is that particular thing in particular unit at which the chemical shift is expressed uh, in terms of spectrometer's fundamental operating frequency. I can give you a few seconds to think about the answer. Is it parts per billion? Is it parts per billion? Million? Is it parts per trillion? Or it's none of the above? Okay, I think you guys got enough time to think about the answer. The answer to this question is parts per million. So it is parts per million. Okay, so the chemical shift is expressed in terms of parts per million. So every time we plot your, we analyze the data with respect to how much of parts per million of what actually shift happens in the material. Okay, Now let's go to the next question. The chemical shift is mathematically defined as. Thus, we need to get a mathematical definition of chemical shift. I'll give you a few seconds for you guys to just think about what this chemical shift actually is and just get a mathematical definition of what actually that is. I'll give you a few seconds and I will let you know the answer. Okay, so let me discuss the answer with you. The answer is in NMR spectroscopy. The chemical shift is defined as a resonant frequency of an atomic nucleus related to a standard magnetic field. Often the position and number of chemical shifts are diagnosed from the structure of a molecule. So it is basically the resonant frequency of atomic nucleus relative to some standard magnetic field. So you can see uh, from this figure there is a the zero, which is taken as TMS, the shift of the TMS, and every molecule will correspond to some specific kind of shift that actually start from TMS. The TMS is basically zero, and if you take this particular kind of an atom, and which is given in the order of parts per million, and this considering the shift of TMS to be the reference point, and then we consider the shift of the other particles, and there is a well prepared chart which we can use to identify this is for H1 hydrogen NMR. And yeah, so once we have this particular chart with us, we can then compare the shift that we obtain. If we get a particular, say, X shift, then we can say that this shift is corresponding to this particular Y molecule present in it. Okay, or by this kind of some attachments present in the molecule. And in mathematically, the chemical shift, this is the chemical shift, which is represented by the Greek alphabet delta, which is nothing but the ratio of shift in hertz divided by the spectrometer frequency megahertz. So you can see this is megahertz, nothing but 10 raised to 6. So this is why this is um, parts per million. Okay, yeah. Now let us go to the next question. What are the two types of NMR spectrometer? So basically, NMR spectrometer, NMR spectrometer is of two kinds. What are these two kinds of NMR spectrometer that are generally used in by the scientific community? I can give you a few seconds for you guys to think about the answer. Then I will give you the correct answer. Okay, I think you guys got enough time to think about the answer. Answer to this question is continuous wave instrument and the pulse Fourier transform instrument. So yeah, the two basic uh, the two basic kinds of NMR spectrometers are. So these are two basic kinds of instrument that works on two different working methodology. So the first one is CW instrument, which stands for continuous wave, which as the name suggests, there is a continuous flow of mm, RF waves to the system, whereas in pulsed Fourier transform instrument, the electromagnetic wave is provided in a pulsed format instead of going to the uh, complete wave, and it will be focused on just some a very small amount of wavelength. So this and that too for a very short time. This is so these are the two types of NMR spectrometer. One is the continuous wave instrument, the other is the pulse Fourier transform instrument. Now let us go to the next question, which is what is the basic operating principle of CWNMR? So it's actually there is not NMR, it's actually CW continuous wave NMR. So what is the basic principle of this CWNMR? I can give you a few seconds for you guys to think about the answer. Then I will discuss the answer with you. Okay, I think you guys get enough time to figure out the answer. So the answer to this question is the CWNMR, which is also which we have already done this. It's a continuous wave NMR. So CWNMR, which is a continuous wave NMR spectrometer operates by modulating magnetic field intensity by using a constant radio frequency signal. The continuous wave device continuously alter the magnetic field, scanning the spectrum of from downfield to upfield. Downfield is a region where the strength of the field is low and upfield is where the strength of the field is high. So basically, the CWNMR operates by modulating the magnetic field. It modulates the magnetic field intensity by using a constant radio frequency signal. This the continuous wave by scanning the spectrum from downfield. So this has to be remembered. It actually scans from downfield to the upfield. So this is the basic operating principle of a CW number. Now I think let's move to the next question, which is a CW instrument dash happens when the stimulated nuclei do not have enough time to return to their equilibrium condition before the instruments field and move to a new location. So what happens? The question is, what happens in a CW instrument when the stimulated nuclei doesn't get enough time to return to this in equilibrium condition before the instrument field is field and uh, yeah, then move to a new location. Can give you a few seconds to think about the answer. Then I'll give you the answer. So I think you guys got enough time to think about the answer. Answer to this question is ringing. So this is a particular effect that is visible. It's called the ringing effect, and this happens when the stimulated nuclei doesn't get enough time to return back to its equilibrium condition. So yeah, okay. So I think now we can go to our next question. Next question is a true or false question, and the question is: the relaxation rate of a stimulated nuclear is lower than the scan rate. You need to know about the relaxation rate of a stimulated nucleus if it is lower or if it is actually faster. So the relaxation rate of a stimulated nucleus is slower than a scanner. Is this true or false? I'll give you a few seconds for you guys to think about the answer, then I'll discuss the answer with you. Okay. So I think you guys got enough time to think about the answer. The answer to this question is true. So actually, there is this particular effect where uh, there is this the relaxation rate of the stimulator. It is actually less than that of this slower. Like it's actually slower than the scan rate. So as a consequence, the continue to proceed to produce an oscillating and quickly fading signal, which is called the ringing effect. So yeah, so if the relaxation is not so faster, this will produce an oscillating effect, and instead of this signal going to its zero at quickly, it will stay. It will like it will go to its go to its zero state in a much slower, which will produce some kind of rippling kind of thing, something like it, and this is what is called the ringing effect. Ringing effect. Now let us go to the next question. The frequency used in a pulse Fourier transform instrument is dash. So what is the frequency of the radiation that is used in a pulse Fourier transform instrument? So is it 90 millihertz? Is it 90 hertz? Is it 90 gigahertz? Or is it 90 megahertz? Okay, so this is the question. So yeah, I think you guys can think for a few seconds, then I will explain you the answer. Okay, I think you guys got enough time to think about the answer. So let me discuss the answer with you. The frequency of radiation used in a pulse Fourier transform instrument is it is 90 megahertz. It is 90 megahertz. So a frequency corresponding. So the yeah. So as we mentioned earlier, NMR instruments are of two types. One is CW type, another one is pulse Fourier transform type. So in pulse Fourier transform, the frequency of the radiation that is used is 90 megahertz. This much quantity frequency is used in pulsed pulsed Fourier transform instrument. Okay. Okay, now let us go to the next question, which is dash is referred to as the release of multiple frequencies of electromagnetic radiation due to the fact that molecule includes many nuclei. Suppose your material consists of n number of nuclei. So there will be a corresponding release of multiple frequencies of electromagnetic radiation. That is mainly due to this presence of this n number of nuclei. So what does this process refer to as? So this is a very typical question that comes when we are discussing about the NMR spectroscopy. And I can read you the question once again. Dash is referred to as the release of multiple frequencies of electromagnetic radiations due to the fact that the molecule includes multiple or many nuclei. So here, the molecule includes many nuclei. For example, consider methane. Consider methane. In methane, which is CH4. So in this, there are four atoms, and each atom consists of one nucleus. So here there is 1, 2, 3, 4, and 5. So there are 5 nucleus in a CH4 atom. So due to this large number of, or this is multiple, or this is many nucleus, this will result in the release of a multiple frequency electromagnetic radiation. So yeah, what does this phenomenon known as? We need to know the name of this phenomenon. Can give you a few seconds to think about the answer, then I will discuss the answer with you. So I think you guys got enough time to think about the answer. The answer to this question is free induction decay FID signal. So the answer to this question is free induction decay signal is also known as FID signal. So here the answer is FID signal. So yeah, so FID signal is referred to as the release of multiple frequencies of electromagnetic radiation due to the fact that molecule includes many nucleus. So if your molecule consists of say different kinds of nucleus, so which means different kinds of atoms, so that can lead to a release of an electromagnetic radiation at different frequencies, and this phenomenon is called as FID signal. So hope you understood this. Let us go to the next question. What are the major components of a NMR spectroscope? Yeah, so this is a very typical question when we are dealing with the instrument part of NMR. So yeah, so what are the major uh, components of a NMR spectroscope? So I can give you a few seconds for you guys to think about the answer, and I will discuss the answer with you. Okay, I think you guys got enough time to think about the answer. No, the answer to this question is as follows. So you can see a diagram over here. See this diagram. Okay, so from this diagram, we can see there are majorly four main parts. The first one is the magnet. I can see there's a magnet and there's a magnetic controller which can control the electric field generated by this magnetic field. And there is a RF transmitter radio frequency source. Yeah, here there is a radio frequency source associated with this. And there's a detector. There's this detector. And from detector, there is a recorder. So the detector will detect the output signal that we get from the sample, and then this detector will pass this information to the um, recorder, which would give print the result. So that is done by this part. So the major four parts are first one, the magnet. Second one, the RF source. Third one, the detector. Fourth one, the recorder. So these are the four main parts in a NMR spectroscope. So what are they? First one, magnet, then RF source, then detector, then recorder. So I think you guys were able to answer this question. Let's go to the next question. As the field strength varies, the dash of a proton matches the frequency of incident radiation. Okay, so here in this question, it says that as a field strength value, if we vary the strength of the field, then something that is related to a proton matches with the frequency of the incident radiation. Okay, can I read the question once again? Uh, yeah, so the question was, as the field strength varies, what field? The magnetic field. As the magnetic field strength varies, the dash, there is some kind of a property that is related to a proton that actually matches the frequency of incident radiation. So what is that particular thing? I can give you a few seconds for you guys to think about the answer, then I will discuss the answer with you. Okay, I think you guys got enough time to discuss the answer. So yeah, we will not discuss, you actually think about the answer. So the answer to this question is precisional frequency. So we already talked about this precision and frequency. So yeah, so the answer to this question is No? Frequency. Okay. So as the magnetic field strength varies, the precessional frequency of proton matches to the frequency of the incident radiation. Thus, the resonance happens. Okay. Now let's go to the next question, which is a true or false question. And the question is, the deuterium, though being an NMR active, does not resonate along with proton. Okay. Read the question once again. Deuterium, though being NMR active, does not resonate along with a proton. Is it true or false? I can give you a few seconds for you guys to think about the answer. Can I let you know the answer? Okay, so now think you guys got enough time to think about the answer. Answer to this question is true. So actually, this is a very true statement. Actually, deuterium being NMR active, it does not actually resonate with the proton. Okay, so this is a very true statement, and one need to be aware of this. So deuterium, the being NMR, it does not resonate with the proton. Now we need to match the numbers. So what does this one? So yeah, basically this 1, 3, the order doesn't matter. The order doesn't matter, but this 1 and 2 should actually correspond to each other. 3 and 4 should correspond to each other, and 5 and 6 should correspond to each other. So here you have this parts per million. We need to see how like higher frequency will move towards a lower parts per million, or a lower frequency will move towards a lower parts per million or chemical shift. Okay, so this is basically how does chemical shift, how how these factors affect the chemical shift. So that is what is actually meant by this question. So how does the higher frequency affect the chemical shift? How does the shielded and unshielded shielded electrons affect the nucleus, affect the chemical shift? How does the upfield and downfield affect the chemical shift, etc.? So I can give you a few seconds for you guys to think about the answer, then I'll discuss the answer. So this is a bit difficult, so I know this, but yeah, just try for a second, then I will definitely help you guys with this question. So yeah. Okay, I think you guys got enough time to think about the answer. So the answer to this question is one can be corresponds to downfield. So downfield, downfield actually corresponds in a lowered chemical shift, whereas two corresponds to mm, upfield. So this will actually increases the chemical shift. Okay, and third one corresponds to the shielded electrons would also reduces the chemical shift, and the fourth one corresponds to deshielded. The uh, deshielding effect will also increases. This actually what it will do. This will actually increases the chemical shift to a higher value. And the fifth one is lower frequency. Lower frequency will reduce the chemical shift. And the sixth one is higher frequency. Higher frequency will actually increases the chemical shift. Higher frequency will actually increases the chemical shift. Yeah. So when we are considering this, we are having two sets of things. Uh, we are having two sets of things. Ones that actually increases the chemical shift, and the other one actually decreases the chemical shift. Then we can categorize it as downfield will actually okay. The upfield actually increases the chemical shift, whereas the downfield actually decreases the chemical shift. Now the unshielded or deshielded effect body actually increases the chemical shift, whereas shielded would actually decreases the chemical shift. Now uh, higher higher frequency would actually increases the chemical shift, whereas lower frequency actually decreases the chemical shift. So these are the things that actually actually have an effect on the value of chemical shift that we observe for a sample when we do an NMR spectroscopy. So I think you guys understood this question. Now let us go to the next question, which is what are the factors that affect the chemical shift? So this is going much more beyond that. So what are the factors that affect the chemical shift? I can give you a few seconds for you guys to think about the answer, then I will explain the answer to you. So I don't need to explain the answer right away because I need to give you guys a few seconds to think. So only after that I will explain you the answer. Yeah. So I think you guys got enough time to think about the answer. So that's it. The question is the It's actually here. The electronegativity effects, the hybridization effect, the hydrogen bonding effect, and the effects of the electronegativity of the particles will actually affect the determines the chemical shape. The hybridization of the particles, like if how like to which atom, for example, to which sp3, to what it is bonding, and all those things actually determines the chemical shift, and the presence of hydrogen bonding in the system will actually determines the chemical shift, and the use of the solvents will also affect the communication. So the answer is first one, electronegativity of the substitutes added. Second one is the hybridization. Hybridization. The third one is the hydrogen bonding present in the system. The fourth one is the nature of solvents present in the system. So these are the four major things that actually affect the chemical shape, which is represented as delta, the unit of chemical parts per million. Okay, so I think you guys understood this question. Now let me move to the next question. This is a true or false question. So state true or false. The chemical shift actually increases in direct proportion to electronegativity of the element linked to hydrogen. So this is a very general question. So what happens to the chemical shift? Will it actually, is it actually proportional to the electronegativity of the element that is actually linked to it? If you have a molecule and you have a hydrogen, and if there is something that is linked to the hydrogen, if some atom is actually linked to the hydrogen atom, and how does the electronegativity of that particular atom determines the chemical shift? Is it directly proportional, or how does that thing actually works? So yeah, I can give you a few seconds to think about the answer, then I'll discuss the answer with you. Okay, now I think we can discuss the answer with you. So the answer to this question is actually true. So actually, yeah, this is actually true. The chemical shift actually, it is proportional to the electronegativity of the element that is linked to the hydrogen. Now we can move to the next question, which is also a true or false question. The spin splitting result in the interaction of nuclear spin of hydrogen atoms to the adjacent carbon atoms. So I can read you the question once again. The spin splitting result from the interaction of nuclear spin of a hydrogen atom result on an adjacent carbon atom. So I can give you a few seconds to think about the answer, then I will discuss the answer with you. Okay, I think now we can discuss the answer. So the answer to this question is true. So actually, yeah, it is true that the spin splitting actually result from the interaction of nuclear spin of the hydrogen atoms with nearby carbon. So when there is an interaction between these carbon atoms with the nearby hydrogen atom, it actually results to a spin splitting. Now let us go to the next question. So what are the reasons for carbon-30 to be found to be about 66,000 times less powerful than the proton resonance? So actually it is, the carbon-13 is actually 6,000 times less powerful than the proton resonance. So what could be the reasons for that? So there are majorly three reasons. I hope you guys can figure it out. Just think it for a few seconds, then I will give you the answer. Yeah, I think you guys got enough time to think about the answer. So the answer to this question is carbon-13 is actually this carbon-13 is pretty rare in nature and it accounts only for 1.08% of our. So this is one of the major merits. First, carbon-13 spectrum, the spectrum that has been constructed from a group of molecules which contributes to just one carbon atom. And the carbon-13's chiromagnetic ratio is much less than that of the hydrogen. So these are the few reasons why carbon-13 is seems to be much less powerful than proton resonances. Now let us go to the next question. The majority of organic functional groups have a signal in between, say 0 to 100 parts per million, 100 to 200 parts per million, 0 to 220 parts per million, 100 to 220 parts per million. I will read the question once again. Majority of the organic functional groups have a signal between 0 to 100 parts per million, 100 to 200 parts per million, 0 to 220 parts per million, and 100 to 220 parts per million. Think of it for a while, then I will give you the answer. Okay, I think we can now discuss the answer. The answer to this question is 0 to 220 parts per million. Now let us go to the next question. This is a match the following question. The saturated have so correspondingly match this side with the parts per million, which is the chemical shift. What does the aromatics have? What does the carbonate have? What the electronegative species have? What the saturated species have? So just think about for a few seconds, then I will let you know the answer. Okay, now I think we can discuss the answer. So answer the question is one, the saturated species will have chemical shift in the range 80 to 60 picometer. The electronegative species will have a chemical shift in the region 40 to 80 picometer, and the aromatics um, would have this chemical shift in the region 100 to 175 picometer, and the carbonate will have a chemical shift in the range 155 to 220 picometer. So these are the answer. Saturated corresponds to 48 to 60. Electro Electronegative corresponds to uh, 40 to sorry corresponds to 40 to 80 band, 80 picometer. Aromatics aromatics actually it corresponds to 100 to 175 picometer, and carbonate groups actually represent 155 to 220 parts per million. I hope you guys were able to answer the question. Now let us go to the next. NEOSY stands for, this is a very easy question, so I can just directly tell you the answer. This is an abbreviation for nuclear oversourcer spectroscopy. Okay, so NEOC stands for nuclear oversourcer spectroscopy. Now let's move to what are this? What is this use of? What is the use of NEOC experiments? These NEOC experiments are mainly used to identify whether a signal originate from protons that are spatially near to one another but are not bounded. So if we have two protons and we can get an idea about if they are bounded or just they are spatially separated from each other through this noisy experience. The noisy spectrum is produced by spatial correlations in form of spin lattice vibrations. Additionally, noisy may detect chemical and conformation exchanges. So these are the basic use of this noisy experiments. Now, what are the axes in a 2D NMR plot? So yeah, in 2D NMR, as the name says, there will be two dimensions, and what are they? So can think for a while, then I will let you know the answer. Yeah, I think we can go forward. The answer to this question is it actually correlates the spectrum of 13CH1 correlation. Yeah, actually on the one side it will corresponds to hydrogen, which is a proton, and the other side it corresponds to carbon 13. So these are the two axes that basically it depends on. Now we have what are two major factors that influences the chemical. We have already seen different factors. This is much more. And the answer to this is de-shielding and anisotropy of the magnetic fields. Now, thank you for your kind attention. I'll be here for yet another 5 minutes. if you have any doubts, please ask me. I can clarify your doubts. Yeah, let me wait for 5 more minutes and let me know if you have any kind of doubts so that I can answer your questions. So if you guys doesn't have any further doubts or questions, then let me wind up this class. So today we have discussed about the NAMA spectroscopy, and in tomorrow's class or in the next week we will discuss the further lectures that will be taught by Professor Tamal in his course. Do follow his course, submit your assignments on regularly, and try to write the exams. So if you have any further doubt, kindly contact me on the next class. Mm, Hope to see you all the next week. Thank you.